All right. Welcome. Sorry about that. I started reading the problem and I realized I was still on the title card on OBS because I'm new and I don't know what the hell I'm doing. So welcome. So let's start. Let's get started on day 25. Combo breaker. All right. You finally reached the check-in desk. Unfortunately, the registration systems are currently offline, and they cannot check you in. Noticing the look on your face, they quickly add that tech support is already on the way. They even created all the room keys this morning. You can take yours now and give them your room deposit once the registration system comes back online. Cool. Okay, the room key is a small RFID card, as is typical, I think, for hotels now. Your room is on the 25th floor, and the elevators are also temporarily out of service. Man, this vacation. So it takes what little energy you have left to even climb the stairs and navigate the halls. You finally reach the door to your room and swipe your card, and beep, the light turns red. Man, all these problems. I fought crabs to be here. Or I guess a single crab. This is more of a card game, but it's okay. Examining the card more closely, you discover a phone number for tech support. Hello, how can we help you today? You explain the situation. Well, sounds like the card isn't sending the right command to unlock the door. If you go back to the check-in desk, surely someone there can reset it. Still catching your breath, you describe the status of the elevator and the exact number of stairs you just had to climb. I would count them too. Okay, I see. Well, your only other option would be to reverse engineer the cryptographic handshake of the card does with the door and then inject your own commands into the data stream. Naturally. You thank them for their time. Fortunately for the door, you know a thing or two about cryptographic handshakes. The handshake is used by the card and the door. Involves an operation that transforms a subject number. Okay, these sound like key terms that I'm not really familiar with. To transform a subject number. This is probably some crypto stuff that I just have never looked at. To transform a subject number, start with the value 1, then a number of times called the loop size, perform the following steps. Okay, set the value to itself, multiplied by the subject number. Okay, set the value to the remainder after dividing the value by 2020, 1227. The card always uses a specific secret loop size when it transforms a subject number. The door always uses a different secret loop size. The card transforms the subject number of 7 according to the card's secret loop size. The result is called the card's public key. The door transforms the subject number of 7 according to the door's secret loop size. The result is called the door's public key. So the card has a public key, the door has a public key. And they each have a secret loop size. That's interesting. The card and door use a wireless RFID signal to transmit the 2 public keys, your puzzle input, to the other device. Now the card has the door's public key and the door has the card's public key. Because you can eavesdrop on the signal, you have both public keys, but neither device is loop size. Okay. The card transforms the subject number of the door's public key according to the card's loop size, and the result is the encryption key. So I think this is like one of those weird key exchange things, right? And I remember reading about this a while back and like having it explained as like you both have a secret paint color and you both have a known paint color, and then you can exchange them and then you mix them and you send back the other colors, and anyway. Man, I wish I could remember the details of that now. The door transforms the door does it too. If you can use the 2 public keys to determine each device's loop size, you will have enough information to calculate the secret encryption key that the card and door use to communicate. this would let you set the unlock command. For example, suppose you know that the card's public key is bleh. With a little little trial and error, you can work out the card's loop size must be 8, because transforming the initial subject number of 7 with a loop size of 8 produces that. Okay. Then suppose you know that the door's public key is blah. By the same process, you could determine the door's loop size is 11, because transforming the initial subject number of 7 with a loop size of 11 produces blah. Okay, at this point, you can use either device's loop size with the other device's public key to calculate the encryption key. Transforming the subject number of blah, the door's public key, with a loop size of 8 produces the encryption key blah, which is completely new. Okay, transforming the subject number, okay. So, all right, well, how are we gonna do this? Let's think. Let's make a new folder. Let's do the usual stuff. Day 25. New file, the coffee. All right, day 25. Combo breaker. Okay. So the handshake is like this: set the value to itself multiplied by that. Okay. Works like this. Let's make this a list. Okay, and cool. So we've got these examples here. All right, let's set up our normal stuff where we define things, we test things, and then we run the thing. Okay. And I guess what we could do is we could just pull in log, and we'll bring in assert. Cool. So let's set up our inputs. Let's grab our inputs from here. You know the card's public key. Let's read it with line breaks. So what is our input again? Our input is both public keys, right? Find your puzzle input. Yeah, the 2 public keys, and let's just see what format we get them in. We just get two numbers. Okay, so let's set up our example with the 2 public keys. Card's public key is this, and then the door's public key is that. So door p key equals that, and then we're gonna have, no, that's the card, and then we'll have door public key equals, let's see, p key doesn't even like, here, let's say card key, door key. Okay. I guess what we can do is we can put them in as input, and we'll have door key. That way when we have to parse it and everything. So that's gonna be our input. Okay, the subject number of always 7, or is the subject something we need to find out? I think the subject number is always 7. Suppose the card's public key is blue with a little trial and error. You can work out the loop size must be 8. So let's, I guess we're going to need to recreate these steps. The card transforms the subject number of 7 according to the card's secret loop size. Secret loop size. So set the value to itself multiplied by the subject number. Set the value to the remainder after dividing the value by that. Okay, well, let's say loop equals, oh, that's a keyword. How about, this is gonna be one transform, and we're gonna take in So value, subject number. So value is gonna, I think it starts at 1. Is that the start with the value is 1? Okay. And then, and it transforms a subject number 7, I think. I don't know if that's hard coded as 7. And then, I don't know if this has a name. I don't know. Let's put it in here. So the card always uses a specific secret loop size. Okay, so this is the loop size that we need to figure out. And the loop size, I think, is just the number of times we do it, according to the card's secret loop size. So this multiplied by the subject. A number of times called the loop size. Okay. Yeah. Loop size equals. Yeah, this is the question: is how many times are we going to transform? Maybe what we'll do is we'll just have transform be one iteration, and then. Okay, so. Okay, so the value to itself multiplied by the subject number equals val times subject. Okay, and then set the value to the remainder after dividing the value by blah. Okay, and then val equals the remainder. Okay, so val after dividing mod that. Okay. So I guess we could just do this. And this is a loop. So value to itself multiplied by the subject number. Okay. And then we set the value to the remainder after dividing the value by. Okay. So this is it, value. And then we want to generate, I guess what we want to do here is we want to generate the private key. Now the card transforms the subject number 7 according to the card's secret loop size. The result is called the card's public key. So what we want to do is we want to find loop size, and we're going to pass in the value. No, not the value. We're going to pass in, what are we doing? The subject number? They both have the same subject number. So what we're going to do is we're going to pass in the public key, P key. And this is going to equal some number. And so what we're going to do is we're going to just transform. We're going to call transform until we get to the key. So key equals, I guess, the number of loops that it takes to get there. Is that all? Okay, let's try that. Okay, loops equals 0, and then until. Is it gonna constantly grow? No, it's not. It's just gonna bounce around a lot. So I guess we're just gonna have to trust that it hits this number eventually. So until what we're gonna get back is we're gonna have the number of loops. We're gonna increment the loops plus equals 1. And then at the end, we're gonna reply with loops and get out of there. I don't know why you're there. Go up there. Okay, so we're gonna start with 0 loops. And then we're gonna say until value, or I guess loop size is key. And this is how we're gonna get the loop size. So we go loops plus equals 1, and we're gonna transform loop size. I'm going to say loop size equals transform loop size. Oops. Yes, we can just say loop size is 1. You can start with a loop size of 1. So I guess, well, loop, no, this is not loop size. Loop size is the number of loops. So loop size equals 0. So until loop size is key, no, it's until value is key. Value. So, and we're gonna come in with value equals, I don't know, 0. I guess value should equal 1. And then it's until value is key. Okay, so until value is key, we're going to increment the loop size and we're going to transform the value again. We're going to start off with a value of 1. So find loop size. We're also going to need parse input. Parse input. All right, this is going to take a wall of text, as it always does, and it's going to just be, what's that? We're going to say card key, this card public key, and door key. Door key. Okay, equals, that's me. Text dot. Okay, equals. Yeah, let's put it on its own line. Text split, new line, and we will, I should indent these a bit. And then we're gonna map it through parse float. So let's see what we get for parse input. I've selected everything and sometimes it just does not like to unselect it for something. I don't know why I've got this number in here. Okay, let's log parse input and see what we get. Cool, so those are the numbers. And then what we're gonna do is we don't need to set that equal to anything. It's just card key and door key. I guess what we could do is we could reply with, so no, that's fine. It's fine to give us back an array. Card key and door key. We don't need to set these equal to something here. So this is going to give us back a card key and a door key. And what is it that we want to find? We want to find, for each one, we want to find the result as an encryption key. Okay, the card transforms the subject to number of the door's public key according to the card's loop size. Okay, so we want to find the loop size, which we got here. And you know what? We're doing this camel case for everything else, so we may as well do it here. So we got loop size. Actually, you know what? Nah, screw that. Let's go snake case. I like snake case. Okay. Okay. So we're gonna have a couple things. So I guess what we should do is we should test that we can find the loop size. So let's find the loop size for this. Let's log find loop size. Let's see if it blows up. It does. Key is not defined. Is picky. Val is not defined. Value. Here, how about val? 8. And is that what we wanted? We could see that it is cards loop size is 8. Okay, and then what if we do the other one? 11. Okay, beautiful. So that's cool. Let's assert 8 is, and let's assert, and we'll assert that 11 is that. So that's those working. Cool. That's pretty straightforward. So we've got the loop size, and that's what we want to find from the inputs. So we've got the inputs, we can parse them. We want to find each one's loop size, and then we want to multiply them by each other. So that's going to be, I guess we can multiply either one. The card transforms the subject doors. The result is the encryption key. And the door transforms the subject number of the card's public key according to the door's loop size. The result is the same encryption key as the card calculated. So if you can use the two public keys to determine each device's loop size, you'll have enough information to calculate. Okay, for example, suppose that you know the card's public key is blue. With a little trial and error, you work out the card's loop size must be 8. Then suppose you know, okay, you know its loop size is 11. Okay, at this point you can use either of the device's loop size with the other device's public key to calculate the encryption key, transforming the subject number, the door's public key, with a loop size of 8 produces the encryption key. Okay, so I guess what we need to do is we need to assert that it works both ways. Okay, what is the encryption key? What encryption key is the handshake trying to establish? I guess either one would work. Find key or find. I guess this is really it's the private key, or I guess it's the shared key in this case. They say public key and private, or they say private key, but I mean really it's like a find shared key. And we're gonna take card key and card key. Card key. Sorry, I think that's a very British joke. Card key and door key. And we'll just indicate to future us that these are numbers. And so what this is going to do is we're going to say, I guess, find loop size. So find loop size card key, and we're going to, what do we multiply that? Transforming the subject number. So do we have to put this through transform? Yeah, I think we do. Transforming the subject number of whatever with a loop size of 11. Okay. And then we're going to, so that's the loop size, and we're going to transform door key with loop size of the card key, and that should be the shared key. And this can just be, I don't know, find loop size, find shared key, sure. So let's assert this as well. Let's log find shared key of, and I guess we can just parse input, but we'll want to blow that out. So 1053, is that right? No, it's not. Transforming the subject number, the card's public key with a loop size of 11 produces the same encryption key of, so maybe it's not transform that I want to do. So card key, door key. So that transforms door key from card key. Let's try the other way. Card key and door key. Are these backwards? No, they're not. They don't. Maybe my transform is wrong. So at this point, you can use either device's loop size with the other device's public key to calculate the encryption key. Transforming the subject number of, so let's just try these and see if this produces, so transform that, the doors with a loop size of 8. So transform, it's a long transform of that with a loop size of 8. Okay, so that's giving us the same answer we were getting earlier, which makes sense, but is also wrong. Produces the encryption key. So transform must not be doing what I think it should be doing, or maybe we've got our transforms mixed up. The handshake used by the card involves an operation that transforms a subject number. So to transform a subject number, start with the value 1, then a number of times called the loop size. So start with the value 1. So this is where I think I've gone off the rails a little bit. Then a number of times called the loop size perform. Okay, set the value to itself multiplied by the subject number. So this is, so transform I think is wrong because it's starting with a subject number. Oh, and I want that to be the thing. Okay, so let's, so transform, where do we call transform? So we call it in find shared key. So that's the value, and then the subject. So the value is 1, and the value should always be 1. It's the subject number that changes. So find shared key, and this transforms the value with subject number of 7. Okay, so here what we want to do is we want to find loop size, and we want to transform loop size. That's find loop size. So I think I've got, okay. Value to itself multiplied by the subject number. So I think this wants us to substitute these for the subject number. Subject number of, okay. And this should be transform. So is it just 1, comma, card key? But then where does this loop size come in? Is this the number of times we need to do it? Maybe. Yeah, maybe that is. So find shared key. Let's try that. Yeah, maybe we need to do this, the loop size for I in 0. Let's do that. Oops. Loops equals that. Always, if I can prevent parentheses, then I'm doing it right. That's my secret. And then we're gonna val equals, let's say val equals 0, equals 0, and then we wanna do right. We want to value equals transform value. So value. So we can start at 1. We can say val equals 1 here, and we can say val equals val card key, and then we return val. So 148. Yeah, this is what we want to do. This is how we find the shared key. So we find the loop size, and that's the number of times we do this. It would be really nice. I really like Ruby's times thing. Like I can do like find loop size, dorky times, and then run a block. I wonder if JavaScript has something like that. I don't think it does. That would be nice though. Okay, so we got the card key, door key, and then the seed value, which is 1. Okay, and that's producing this number, which is good, and that's what we want to do. We want to assert this guy is the shared key of the input, and that's what it is. And then I guess what we could do is we could check it backwards as well. So that's door key, card key. So let's try card key, door key, and it's still working. Beautiful. In fact, I can do this. In fact, I can, no, still need to return value. Yeah. I'll just leave it like that because I think it reads better. So loops equals find loop size card key for I in 0 up to and not including loops. Update the value by transforming it. Okay, cool. So we've got our test input. we're asserting that these things work, and I guess what we want to do is we want to find the shared key for the actual input. So let's do that. Require input, which we will need to get here. And new file, call it input.coffee. Module.exports. Okay, let's run that, and I guess we need to log it. So this is the number that we're getting, and let's feed that in and see if they like it. That's the right answer. All right, 1 gold star closer to saving our vacation. Continue to part 2. Here we go. Part 2. The light turns green. Light turns green and door unlocks. As you collapse onto the bed in your room, your pager goes off. It's an emergency. The elf calling you explains. The soft serve machine in the cafeteria on the sub-basement 7 just failed, and you're the only one who knows how to fix it. We've already dispatched a reindeer to your location to pick you up. I could have just taken the reindeer the whole way. It's like Lord of the Rings. I could have just flown the eagle there. Okay. You hear the sound of hooves landing on your balcony. The reindeer carefully explores the contents of your room while you figure out how you're going to pay the 50 stars you owe the resort before. They're going to take all my stars. Noticing I worked so hard. Noticing that you look concerned, the reindeer wanders over to you. You see that it's carrying a small pouch. Sorry for the trouble, a note in the pouch reads. Sitting at the bottom of the pouch is a gold coin with a little picture of a starfish in it. Looks like you only needed 49 stars after all. You have enough stars to pay the deposit, although it hasn't changed. You can still get your puzzle input. What? Pay the deposit. You spend all 50. Oh, is that it? There is no part 2? To cover the room deposit. As you fix the soft serve machine, Santa offers you a ride in a sleigh. Maybe the resort has a chimney you can use. Cool. All right. I guess, was that it? We got both stars for day 25. There was no part 2. Woo! Here comes Hurricane WebGL. Nice. I like it. Maybe it's Hurricane CSS. I can't tell, but you know what? It's awesome. All right, cool. That is it. That means that there is no part 2. So just remove that. Cool. Yeah, that was fun. I really enjoyed that. I enjoy it every year that I do it. I guess if I'm craving more, I can go back and do previous years that I haven't done yet. Like, for instance, 2019, I haven't done it all. I think 2018, I think I did a few and fell off. It's common thing is you just like sort of like get distracted and then forget to go back. But I really do enjoy it every year that I do it. So that's yeah, that's day 25 in the bag, and that's Advent of Code. I guess what we can do is we can go back and we can take a look and see if there's anything we want to refactor here. I don't think there is, though. There's not a lot going on. Parse input does a very small amount. It's very, very common across all our code to have this kind of parse input. Find loop size. So we take in the private key, we take in, or we just initialize loop size and value, because really that's all that we do here. And then find loop size, just, yeah, find card key. And I guess what we could do is we could initialize the value here, but we don't need to because we just call transform directly. So find loop size and value, I mean, they don't really interact. And then transform, and this couldn't be that much simpler. I was thinking about moving the subject to the first argument and having the value as the second, but didn't need to do that. And I don't think it makes anything particularly easier to read. I mean, this is literally what we're doing. Find shared key, and we give them the input, and it works it out. So that's fine. Yeah, I think we're good. I don't think there's anything to do except push this up And that is that's it. That's all we got going. Thanks to everyone who followed along and helped me out in the chat, especially Blake and David for showing up multiple times to bail me out of a mental mess. Appreciate you guys. Thank you very much. When all this COVID stuff is over, owe you guys something fun, something delicious. So yeah, anyway, I guess that's it for Advent of Code 2020, and maybe I'll make more videos that aren't Advent of Code, but probably not live coding. Maybe, I don't know, if I can think of anything that I wish I had learned in a way that isn't immediately obvious, maybe I'll make a video on that. But anyway, until maybe next year or whatever, thanks very much, and happy